Okay, now it's time to talk about protein engineering, specifically about sequence space, rational design, and directed evolution. What does it mean? What is the concept of sequence space? And what are the differences between rational design and directed evolution? Let's first have a look at sequence space. What really is sequence space? Sequence space is a function that represents all possible residues inside of a protein or enzyme and their functionality. So here we have an example. On the right hand side, sequence space, the function, is obviously dependent on the protein size, so how many amino acid residues are inside of your protein, and also what does functionality really mean. This could, for example, mean that you assess one functional parameter such as enzymatic activity or thermostability or folding stability. All of these parameters fall into the category of functionality, and depending on what you want to assess, these are also represented in sequence space. So on the right hand side, as I said, we have an example, and this is a 3D simplification, so to say, of sequence space. So we just assume that this graphic right here represents all of sequence space for one specific case, for one specific protein. But if we were to dissect this in reality, we see that we have three axes, right? So this means that we have here a plane of all possible dipeptides. So this is for example, the first position of all amino acids, and this would be the second position of all possible amino acids. And then this would be one functionality parameter. So in this case, we say that high functionality or high activity, let's call it, is very good. So we see that these peaks are very good, and these troughs are not very good. So we want to search a protein, an arbitrary protein that is high activity. We say that this represents a standard protein about the size of 200 to 300 amino acids, but we remember in reality these only represent peptides, dipeptides, so of length 2. Okay. It's also important to note that sequence space is discontinuous or rigid. So because our axes for the amino acids are nominal, so we have, for example, 1 point for lysine, 1 point for arginine, 1 point for serine, and so on, we do not have a really continuous function between those points in the plane, right? So we just show these by these rather harsh edges of sequence space. Now we can ask the question, what is protein engineering? And here I have drawn an example into the sequence space. Protein engineering is the controlled evolution in sequence space. So you could, for example, say you have a protein at a starting point right here at position 1, but your protein is not good enough for you. You want to design a protein or an enzyme that has a very high activity, so that it improves a problem, that it improves your process. And what you want to do optimally is you want to take as few steps as possible to find this optimal protein. In evolution, this process happens naturally, continuously. There are mutations that force different proteins, different variants to take different steps. Some of them are a little bit improved, therefore they have the possibility to improve even further, and so on and so on. But in the laboratory, you would have to make some sort of mapping of these possible trajectories. This red line here is a possible trajectory. So this is a sequence of possible variants that you could generate from each other until you arrive at a point where you decide that you want to stop. Now there's a problem. The normal protein has, let's say, or the normal standard enzyme has usually 300 amino acids, something around the lines of that. Which would mean that for any specific protein of this size, there would be 20 to the power of 300 variants. Obviously, you cannot test all of these variants, right? This is a pressing problem, a computational problem, because you need to make very good guesses to decide which way you want to go. It could, for example, be that you improve at every step, sort of like here. You could say these variants improve a little bit at every step. So in a directed evolution campaign, for example, you would find them very easily. Don't worry, we get into the technical terms on the next slide. But for example, it could also be that you'd have to descend first, so that you have to generate a variant that has decreased activity, but then you are rewarded by finding a variant with higher activity. This is not the global maximum in this case, but there could be a chance where you couldn't tell the difference. If you arrive at this point, you wouldn't really know if you are at the global or local maximum of the function. So it is not guaranteed that in each possible case you will find the total global maximum of the sequence space. So we cannot only just say, let's just choose improve variants and try to improve them further. We have to find some sort of smart way to predict what is going to happen in the next round of experiments. Okay, let that sink in. Now we want to think a bit more conceptually about directed evolution and rational design, the two examples, so to say, the two types of thinkings which protein engineering is approached. All right. So let's start at the common point. Some sort of improved variance. This is what we are looking for, right? A directed evolution campaign uses a technique called random mutagenesis. So you randomly generate variants, and these are then formed, or they make up a protein library. So you have, for example, hundreds or thousands of different variants that you have generated randomly, and then you screen among those for improved variants. And these variants are then susceptible again to random mutagenesis to try and find new protein libraries, to try and find new improved variants. And at some point you can decide to stop, essentially. So what this means is directed evolution represents a sampling of sequence space. Let's go back to this slide here. You basically have a starting point. You generate random sequences all around sequence space here, like near neighbors of this sequence. And you randomly sample and say, okay, this could be a hit, this could be a hit, this wouldn't be a hit. Something like this. But it's not that simple. As I mentioned earlier, you could also generate better variants after you have some sort of decrease in activity. You have to keep that in mind. And then you would say, okay, these and these variants were very good. Now we start again. We do a sampling from this position. We do a sampling from this position. And so you gradually march your way through sequence space to try to find improved variants. On the other hand, there's the concept of rational design. So if rational design would be completely possible, so let's say you would know everything about proteins, you would know how they evolve, you would know which amino acids have exactly which effect, then you wouldn't need to sample sequence space. You could just calculate or tell which sequence would be the best for a specific kind of use, right? This is obviously not the case. As I said before, very complicated, because there are so many variants that you can never really find a true function of sequence space. But just conceptually, let's have a look at it. Rational design would not use random mutagenesis, but site-directed mutagenesis, because you would know exactly where you want to have the mutation occur. These site-directed mutagenesis would be introduced based on models and predictions that you have made previously to design improved variants, right? These models and predictions, or rational design, could be determined as representing the fundamental rules of sequence space. So you have some sort of insight from sequence space, which are then turned into a model. And this model helps you to design protein variants. In reality, often a combination of rational design and directed evolution is used, right? Rational design, or parts of rational design, are very useful because they drastically can reduce the amounts of samples that you need to make to find an improved variant. This approach, this combined approach, is called the semi-rational approach. Okay, now let's have a look at three very important phenomena in sequence space. Let's just conceptually explore them a little bit better. I already mentioned this before. We already had a closer look at this line right here in our sequence space example. Mutations like this, so these lines here, correspond to one specific mutation. It's the fictionary amino acid X paired with all possible other amino acids acids, right? XA, XB, and so on. In this case here, you can see that the mutation X at that site is always deleterious. So you always end up with a decreased activity or decreased functionality. On the other hand, it could be that a mutation is the opposite. It's globally compensatory. For example, the fictional amino acid Y here, you can see that for all possible amino acids, the functionality or the activity is increased in every possible pairing compared to your starting point. But now you can see here there's a clear line, every activity is 0 right here, and here it's not clear, right? So still you have higher activity in this region than you have in this region here. And there we come to probably the most important phenomenon of sequence space, which is also related to the question why it is so hard to make predictions about the evolution of proteins, or about the function of proteins even. This phenomenon is called epistasis. Epistasis originates from a genetic context where it describes the non-additivity of effects of mutations. And this is the same as it does here. So let's have a look at this example picture. We can see that we have one mutation here, which is called W, and it is paired with some amino acid R. And then we also have one right here that is called Z, and it's also paired with R, right? And we can see that that those two, if we were to say this would be our starting point here, we start, let's say, at 0 activity, and we mutate now both variants. Then we see we have a slight increase of activity, but overall low activity for both amino acids. Now you would think, okay, maybe if amino acid W causes this amount of increase in activity, and Z causes also the same small amount of activity, then the combination of W and Z would be the combination of both effects. But this is not true, as we can see here. The combination of both amino acids, for example, could result in a much higher, in a non-linearly higher activity. It could also result in an even lower activity. And these are different types of epistatic depending on the context. If they are positive, they are called positive epistasis. If they are negative, they are called negative epistasis, for example. So we can see that the combinations of different mutations and their effects, they do not add up linearly, not necessarily. This is what further complicates the process of predicting the effects of amino acids and also the rational design process of enzymes.